Let's talk about the Earth, shall we? Earth's place in the solar system. So, let's talk about how it got here. There we go. So let's discuss something called the nebular theory. Remember, highest level of knowing, testable, repeatable, never been proven false, widely accepted. So the nebular theory states that the solar system, the sun, the planets, everything else, coalesced out of a swirling cloud of interstellar dust and gas called a nebula starting about 4.54 billion years ago. So everything in the solar system is around the same age-ish, all right? Because it all kind of formed from this big swirling cloud of dust and gas just out in the middle of space. The sun was eventually born in the center. Every piece of material, no matter what it is, particle of dust, a car, a planet, all has an attractive force of gravity. Little physics. So anything with mass has gravity. So out in space, if you have a piece of dust and a piece of dust, they're both made of stuff, mass, they will eventually be attracted to one another. So you have this swirling cloud of dust and gas, which is made of particles too, and eventually started to come together. As that material under the force of the attractive force of gravity started to come together, it started to kind of in the center get packed tighter and tighter and tighter. The more material coming together, the more attractive force of gravity, the more stuff is attracted to it, so on and so forth. So it became so dense, there's so much material that got compacted together under the force of gravity. That is what eventually formed our star, the sun. Turned on. There was so much attractive force that molecules and atoms were forced to fuse together, squish together. That's what turned on the sun. That's why we see the sun as being so bright. There's a bunch of nuclear reaction, a bunch of nuclear fusion going on every second. Atoms of hydrogen are being fused together. It releases a lot of energy when that happens. So that's how kind of the sun kind of turned on. But it's also this nebular theory that not only describes how the sun formed, that's our star, but how the planets formed, why those inner planets are more rocky and solid, and why the outer planets are a little bit more gaseous or made of ice. So, again, here's a visual. So there's just a big cloud of dusting and gas. It started to contract under that attractive force of gravity. As that began to occur, as the stuff began to kind of condense in itself, it began to spin. So now you have gravity kind of pulling things in. But then when you spinning things kind of want to go out. For example, right, here's my little badge, right? The faster I spin it, string kind of makes its way out. There's an attractive force. There's a elastic piece pulling it in, but as you start to spin things, there's another force going on there, fictitious force going on there, that's pulling stuff out. Well, that's what happened to this nebula. Nebula is what you call the cloud of dust and gas on space. So as it started to collapse in on itself, it began to spin, which created a central bulge where the sun eventually would be, but also this disk that kind of panned, that got thinned out. As it continued to spin, the contraction raised the temperature, nuclear fusion begun, turned on the sun, essentially. But the outer disk began to cool. Well, in space, it's cold. As it began to cool down, material started to kind of come together under their own mutual force of gravity. Now this process is called accretion. So this is known as an accretion disk. So now you got the star in the middle, the sun, and now you got individual clumps coming together. Those are what would eventually form the planets. So within a few tens of million years, a blink of a universal eye, almost all of the debris had accreted into today's planets. The inner rocky planets, the outer gas giants, more gas and ice, and then we have an asteroid belt in between. It's the long story short of how the solar system formed. Seems somewhat simple, and then a lot of people ask, well, how do you know? How do you know? Remember, it's the nebular theory, highest level of knowing. Testable, repeatable, never been proven false. How do we know? It's pictures. So this is just different telescopes pointed to different parts within the within our galaxy, within the Milky Way galaxy, and we see it. We see this happening. We see the nebula. We see the point with the stars turn on. We see the accretion disk starting to separate out into what will eventually become planets. We see it. How do we know? Nothing better than saying, "Oh, I got some pictures. Here it is." How can you prove you went to France? Yeah, I got pictures. Oh, okay. Can you prove that this is what happens? Yeah, there's pictures. So that's how it formed. That's how the solar system formed. I know that's a very brief once over. We'll touch on it a little bit more, possibly in class. So when we're talking about the planets forming, so the whole nebula theory is that from this cloud of dust and gas came the solar system. How the planets formed is called planetary accretion or accumulation. So the outer portions of this nebula, when it cooled into these disks of debris, these kind of materials started to clump together under, again, the force of the attractive force of gravity, to eventually form kind of these rings that would eventually clump together to form planets, amongst all the other material we see out in the solar system. That's also why the planets are kind of isolated the way they are. They are forming in these rings, and these rings eventually all clumped up into planets, so it kind of got segmented. There are some stray rocks and stray material out in space that were never drawn in by a force of gravity of anything, and these things became, asteroids, comets, some of the satellites that go around planets, commonly referred to as moons, but technically that's not correct. There's only one moon in the whole universe, and that's the one that we see because that's its name. It's a natural satellite. Just like an artificial, telecommunications satellite goes around the Earth, our natural satellite goes around the Earth. That's the moon. It's its name. That's why, if someone said, "Well, how many suns are there in the universe?" Well, one, because that's the name of our star. So anyway, I'm a stickler for that. So in the solar system, Earth is just one of 8 planets in orbit around the sun. Sorry to Pluto. Pluto is no longer a mainline planet. It is what's known as a dwarf planet, there are actually several of those in our solar system. Also in our solar system, again, over 200 natural satellites, moons, asteroids, comets, meteoroids, and yes, dwarf planets, etc. Just curious, can anybody put those planets in order? Can you name the planets in order? All 8 of them? Anybody remember a rhyme or an acronym? I'll give you a hint. Mvemjasun. Mvemjasun. Mvemjsun. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Not Pluto. So, Mercury, Venus, and Earth make up what's called the terrestrial planets. They're small, but very dense, rocky planets. Then you have the larger gas giants, also known as the Jovian planets, named after Jupiter. Jupiter, Saturn, Uranus, Neptune. These are very large as compared to the other terrestrial planets, but low density, mostly made up of gas and ice. Now, this is not kind of the distance-wise from the sun. This is purely size, scale, to show you how big Jupiter is compared to Earth. So this is just by size. The Earth is not this close to the sun. If we were this close to the sun, we would not exist. All of these planets would be burnt by now. But just to show you the size of the planets also versus the sun. If you can imagine how big the sun is just based on this small slice, the sun is huge. Here's Pluto, way out here. It's way out here in the Kuiper Belt. All right, so it does act a little bit different than some of this other space material out here, asteroids and comets. It is a little bit bigger and it does act a little weird, so we call it a dwarf planet. But there's also one right between Mars and Jupiter. Ceres is another dwarf planet. It's in the asteroid belt, a little bit bigger than most normal asteroids out there, moves a little bit differently, dwarf planet. But again, it's the nebular theory that discusses, well, why are those inner planets rocky, but also the gaseous stuff, the gaseous planets, the Jovian planets, the gas giants, why are they gassing? So that's what I want to get into next. Why are the inner planets rocky, small and dense, rocky, solid? First off, temperature. So the high temperature of the inner solar system when it's forming is about 300 degrees Fahrenheit. And that's hot. That evaporated away any really lightweight elements, gaseous elements, like hydrogen and helium, that really pushed them out. So there was a lot more gas on the outskirts of that rotating disk than on the inside, because the temperature of the sun, once it turns on, really kind of evaporated and pushed those things out, leaving behind really only the heavier elements and heavier compounds closest to the sun. So that's the stuff that eventually clumped together to form these rocky, solid planets. Also, seismic explosion. So when the sun turned on, the nuclear fusion occurred. That's how a thermonuclear bomb works, through nuclear fusion. Well, okay, imagine that times, trillions all at once. There's going to be a large, massive concussive wave, shock wave, kind of sent out from that initial turning on. So again, that may have blown some of that lighter material to the further outreach. It's taken a lot of that lighter elements of gas, hydrogen and helium, and some of those other compounds and molecules, and pushed them out. Whereas the heavier stuff didn't get pushed out as far, right? If I'm trying to throw a baseball or throw a car, I'm going to throw a baseball a lot farther because it's lighter. And then gravity. Gravity is another reason. As that early nebula gas cloud started to rotate, some of the lighter stuff, as everything started to spin, got spun out. The elements can kind of be thrown off from the center, while the heavier stuff didn't travel as far. Plus, heavier chunks of rock were kind of pulled closer to the sun because of the sun's gravity attracting mass. The amount of gravitational force is tied to a few things. One of those is the mass of objects. So if you're going to have a more attractive force if there's two things. Let's say there's a brick and a feather. The brick has more mass. It's going to be have more of a force of gravity than the feather, the lighter feather. So the more mass something is, the more gravitational force. Thus, when everything is forming and all this stuff is spinning around, that less massive gas had less of the sun's pull of gravity pulling it in, so it kind of escaped as things were moving around. As things were spinning around, that accretion disk was spinning around. But the heavier elements that eventually goes into making metal and rocks, it's heavier. It's going to be held closer by the pull of gravity of the sun, closer to the inner solar system. Hence, the inner planets are rocky and metallic, and the outer planets are mostly gas and ice. Fun facts. Anyway, a little bit complicated, but that's why we're on this solid planet of ours. Let's pause here. Now that we've made the sun and we've made the Earth, let's talk about what's inside the Earth. I'll see you back here in just a second.